The design of finite state machine is opposite of the analysis. So instead of having a bunch of flip-flops connected, maybe together, maybe just to a bunch of gates in here, a bunch of OR gates, or maybe XORs, or something like that, some sort of a combinational logic, and then you have the outputs also connected to a combinational logic, and maybe you do have the input directly connected to the output. So in the design step, it's actually the opposite of that, because we usually don't have a logic diagram. We usually have some sort of a word specification, and we know exactly what we want. And what we're trying to do is we will draw a logic or a state diagram like this one here, like S1, S0, and S2. And we're trying to figure out the directions and the arrow and the transition. And you go through a bunch of steps to actually go and figure out what the implementation should be. So the design actually, instead of starting with flip-flops and logic gates, what we do is we start with word specification, and then based on that word specification we draw the state diagram, and we go through a bunch of steps to actually come up with an implementation. So the design of finite state machines, if they're simple finite state machine, can be done manually. However, larger and more practical one that you might see in reality, they're usually done with CAD, kind of like Vivado or Quartus. But understanding the steps that the CAD tool has to go through in order to go from specification into all the way into implementation will be useful. So these steps that you see in here are the steps that I take whenever I'm trying to design a simple finite state machine by hand. There is no standard way or standard procedure to designing FSMs. However, these steps will be useful. So let's go through them very briefly. So the first step is actually you read the specification and figure out what you need, and you draw the state diagram. So you go and you draw like state diagram like this with different states and whatnot. And I'll go through a few examples, but I'm just going to go through the steps very quickly. And then you reduce the number of states if necessary. So we've seen in an example there was a lot of states that are unnecessary, so there's actually some procedures to reduce it. However, for the sake of brevity, I'm just going to ignore this particular step, because in practice, as it turns out, it's not always useful to reduce the number of states. Sometimes it actually overcomplicates the logic diagram that you need for the next state or whatnot. So I'm just going to, for brevity, basically, I'm just going to ignore this particular step. The next state is actually to figure out what the binary value for these states. So these states in here is S0, S1, S2, S3. There's different ways to some sort of a coding them. So you can code them in binary or gray code or any code for that matter. And then after you do this, you usually go and draw the state table. So if you were paying attention, we're moving in the complete opposite direction as the analysis. So now we're going to go to the table with the next state and the inputs and the present state and a bunch of outputs, and you figure out the X and inputs and a bunch of zeros. So you write the state table. And then you choose a flip-flop type. You can implement any of the state machines that we've seen. You can implement them with any type of flip-flop. But for the sake of simplicity, we're just going to focus on D flip-flop in this video, in this whole module actually, and the whole, all of the videos. I'm just focusing on D flip-flop, but the same analysis can be applied to JK and T flip-flops. And then after that, you just have to figure out what the inputs equation for the flip-flop and the output equations. Basically, okay, you figure out what D flip-flops are, use these here to get with the state equations. Okay, once you figure out what the state equations are, you can actually figure out the whole circuit, and you draw the diagram, and you have a full implementation. Okay, so I'm gonna go through these design steps in here using a couple of examples. Actually, we're gonna be designing a sequence detector similar to the one we've seen in the analysis steps. What is a sequence detector? Just a quick review of what it is. It's actually just a circuit that gets some sort of an input, and it samples the input at very particular interval, and that interval is usually connected by the clock or controlled by the clock. So at every active edge of the clock, you're going to read whatever X is, and Y will be asserted if that sequence that you're looking for gets matched. So for example, we're going to build a sequence detector that detects a 1 followed by 0 followed by 1. So whenever you have these sequences coming one at a time, so for example in here, you have 1 followed by 0 followed by 1, this particular detector will output a 1, and then we'll go back to 0 depending on the next input and whatnot. And we will allow some sort of an overlap, meaning like if you see 1 0 1 0 1 0, it will actually output that. So let me show you an example. And frankly speaking, we're going to build that sequence detector with a mealy output and a more output. But we're going to start with a mealy output in here. The very first thing I do when I'm trying to design a new finite state machine is I give myself a few examples to work with just to make sure that I understand the whole thing. So what I went in here is I went ahead and I generated a bunch of numbers and a bunch of outputs. So let me walk you through what these numbers and outputs mean. So here, so we have a sequence detector. So the sequence detector will accept a bunch of x's, and at the each active edge of the clock will just sample that x. So that's what this table here is showing me. So the first thing it will show me is, okay, there's this 0 in here at time 0, which is the very first active edge of the clock. I'm just going to send that x in here, so this is 0. And of course, the output at this point should be 0 because I haven't seen the sequence I'm looking for, which is 1, 0, 1. And I'm designing a melee output in this particular case in here, in this first try. Then the next one in here, you're going to see that I'm sending another 0. So this 0 here gets, well, it was read by the finite state machine, and my finite state machine will see and remember that it went to, and it saw a 0. So the next one here is this 0 now. It will be followed in here. And again, it will actually go in here, and you can see this is at the next active edge of the clock, and you'll see that the output is still 0. And it goes on and goes on. So the next one will be 1, and at that particular case, that one in here, let me just show you. This one in here will be basically seen, and of course I haven't seen that pattern, so this is the second active edge of the clock, or the third one, 0, 1, 2, which is third. But anyway, so what I'm trying to say is in here is that sequence detector is looking for this particular pattern, 1, 0, 1, and because it's a melee machine, the output will be directly outputted to 1, and then it looks for this 1, 0, 1, and they output it in here. And I'm making the assumption or the design decision that overlap is okay. What do I mean by overlap is okay? Well, this is also the pattern I'm looking for. And what I mean by overlap is whatever happening with this particular one in here. So this particular one, I will consider it as part of the last 101 pattern that I detected, and it's okay. And I will also double count it and make it the or the first one in the next one in the next sequence. And that's why you will see that this one is okay. If overlap is not allowed, or I decided not to allow that overlap, so in other words, I don't have a moving window, but I have like a windowed, meaning I will be taking a look at some window like this, and then the next window will be like this. Not like I'm not moving the window one unit at a time. Like for example here, let me show you. For example, let me assume like instead of doing this, I was moving it not moving it one at a time, but moving it 3 at a time, 3 at a time, 3 at a time. In that particular case, that particular output will not be asserted. But I'm making the assumption that overlap is okay. So let's get started and design that particular circuit or that particular finite state machine that will implement this sequence detector. So usually the very first step I do is I say, okay, this is the sequence I'm looking for, and I usually look for that. And I will start with saying, okay, I will have like some sort of a reset state. I will call it S0. And that's basically the very first state. And I haven't seen anything. Sometimes you can see some books on some online website will show you this arrow, and this arrow meaning like whenever you press reset, we're going to go back in here. All right, so now if the input is 0, it's not part of that sequence I'm looking for, so I'm going to just stay in that reset state in here. I'm going to say 0, and like I'm just going to write that the output will be 0 as well because I haven't seen the sequence yet. Okay, what about if the input is 1? Well, the input is 1, it's part of the sequence I'm looking for, so what I'm going to do is I'm going to say, okay, I will define another state in here. In this particular state, I'm going to call it S1, and this S1 in here will tell me, okay, I have seen a 1, and the output is still a 0. And I can technically write on the side the S0 is remembering a 0, and maybe S1 is remembering a 0 followed by a 1 or something like that. Well, let's say it's remembering at least for this particular point, it's remembering the very first one in here. That's what's it remembering. It's seen a 1. Okay, so then we can go from S1 and figure out what happens if you see a 0 or 1. Usually what I do is I go through the sequence I'm looking at. If I'm actually designing a sequence detector, I'll go, well, I'm looking for 1 followed by 0 followed by 1, and that's how I go about it. So the next state in here, I'm going to say, all right, this is basically S2, and in S2, I'm looking for 1 followed by 0, so it's 0, and the output is still 0 because I haven't seen the whole thing yet. And I usually say this is a 1 followed by a 0. Okay, that's what I remember. And of course, if a 1 comes in at this particular moment, then I will have to figure out what to do. Well, if a 1 came in and I'm allowing an overlap, technically I should go back to S1. So if I'm allowing overlap, this is here. I'm not resetting. If I was resetting, I would have 1 here. But because I'm not resetting and I'm allowing overlap, I'm going to say if the input is 1, the output should be 1 at that point because I have seen a 1 followed by 0 followed by a 1. And of course, because of the overlap happens, this actually is just remembering a 1. So if it was followed by a 0, followed by 1, it will be asserted again. And that's basically the state machine that I'm interested in. However, this state diagram is not complete because for S1, if I get a 0, I'll go here. But what happened if S actually is at 1? So I need to actually complete it. And completing it meaning, okay, let me just see here, S0. If I get a 0, if I get a 1, okay, I have that accounted for. S1, if I have a 0, I'll go in here. If I have a 1, well, what do I want it to do? Well, S1 is just remembering a 1. So I'm just going to say, well, if you have a 1, just stay in here and the output should be 0. Let's go to S2 in here. So S2 is telling me if you have a 1, you go back in here. But if you have a 0, I need you to go back probably to S0 is the good option in here. And that will be 0 and the output is 0. And now we have, and I'm just going to highlight the one in here. Now I have my finite state machine, and this is a mealy finite state machine with a mealy output, and that mealy output in here, you can call it 1 or 0 or so forth. And if you have multiple inputs, for example, here I only have an X, so each one of these states will have only 2 options to leave, either 0 or 1. But if you have, for example, 2, you will have 4 of these options, and you're going to have to account for all of them. And frankly speaking, this is the most important step in the design. So we figured out that we need a sequence detector, and we figured out what the state diagram should be. I can technically go and input this in my CAD software using Verilog or any other HDL for that matter, and the CAD software will figure out the rest of the steps for me and figure out the implementation. So this is the important step in here, which is usually done by a human. You can't just offload this to a computer. But the next steps are so mechanical that you can. But anyway, I'm going to go through them just so that you understand what's actually happening under the hood for a CAD software. So the next step usually is reducing. I'm reading it from my notes in here, and you can actually read them on your own in here. It's actually reducing the number of states. I'm going to just not do that for now. I'm going to assign a binary value for these states. So what I did in here is I actually said S0, S1, and S2. There's multiple ways of actually assigning a binary value. The easiest one is actually to assign binary values. For I have three states in here, so 3 states will need at least 2 flip-flops. So I'm going to say, well, S0, I'm going to code it as 0, 0. That's a binary. S1, I'm going to code it as 0, 1. And S2, I'm going to code it as 1, 0. And of course, I'll have a 1, 1, which is unused. And I can account for that on what happens. Another one to do it, this is basically the binary way to do it. There isn't a single one, but for example, a common one is what we call a one-hot encoding or one-hot binary assignment. Instead of assigning like binary numbers for each one of the states, you can say, well, I have 3 states. Let me assign a flip-flop per state. And that means I'm going to just assign one of the flip-flop will be active, the rest will be 0. So S0 will be, for example, 0, 0, 1, and then S1 will be 0, 1, 0, and then S2 will be, for example, 1, 0, 0. So this, of course, will have to, I'm using a little bit more flip-flops in here, but the promise here, if you use another like one-hot encoding, is maybe the next state logic will be simpler or 1-out. Either way, it doesn't matter which one of the encoding you actually do or the state assignments. It's the result or the final function or the final circuit that you're going to come up with hopefully will detect or should detect, functionally speaking, the same exact pattern of 1s and 0s, just implementations are different. And we've seen this in the analysis step now. We've seen several circuits detecting the same sequence. But anyway, for this particular implementation, I'm just going to assign it with the binary numbers. It's just because the table is going to be a lot simpler because I only have 2 flip-flops and I don't have 3 flip-flops, okay? Okay, so the next step in the design procedure is actually figuring out the state stable. So if I've decided to code it with binary, all I have to do is just figure out that I need a couple of flip-flops. I'm going to call one A and the other one is B. And of course, because I have a mealy output or mealy outputs and I have a 1 input, so I'm going to say X0 and X1 in here for the next state. And of course, because I have a mealy output, the mealy depends on the value of X. So I'm going to do this in here. And of course, all I have to do is just say 0, 0. That's the first state. And then I have the second state, or is S1. And then I have S2 in here. Technically, I don't need S3, but I'm just going to write it for the sake of completion. Okay, so now all I have to do is just follow this particular table or this particular diagram to come up with this table in here. So what do I need to do? Well, this one here is S0. It's telling me if you get the input as 0. So the next state will be the same one, which is 0. So I'm going to just say, well, S00. Okay, and now of course you can start writing this table with saying S0 in here, S0 and so forth, but I'm just writing the binary code just to save some time. So in here, I'm gonna say, all right, what about if the next input is 1? Well, if the input is 1 and the current state is S0, the next state is S1. So I'm just gonna say this is 0, this is 1. And I'm just gonna fill out the table as in this particular situation or in this particular procedure. Okay, so I filled that table, and again, these X's are just don't care because technically I don't have a state 3. As you can see in here, I'm using 2 flip-flops, so I have 4 states all the way from S0 to S3. I don't have S3, so I can deal with these as don't care, or you can definitely specify them. All right, so let's take a look about what is the next step. So we figured out what the binary encoded state table is. So now we're gonna have to figure out what the type of flip-flop we're using. If we're using the flip-flop, which is the simplest, all we have to do is come up with like some sort of an input equation, output equation for these flip-flops. Really what I'm trying to say is, okay, you're gonna have to figure out what you need to put for these flip-flops A and B and write these state equations and also the output in here. So what we need to do is we need to say, all right, so I have a flip-flop A and a flip-flop B and only an input X, so that I have 3 different variables. So all I have to do is come up with some sort of a Kmap that actually is a 3-variable Kmap. So I've designed these 3 variable Kmaps and hopefully they're correct. But anyway, so what we need to do is we need to figure out something for flip-flop. Let's say this is for flip-flop A. So I have to take a look at this state table and fill these Kmaps from the state table. So for flip-flop A, I have, based on the value, if this is X, so these are X0. So I'm looking at these particular 1s and 0 pattern. So what I really have is I have a 0, followed by a 1, followed by X, followed by a 0. And for the pattern for X equals 1, it's actually these ones in here. So what I have is I have a 0, 0, X, 0. Okay. And then I can fill out the rest of them. Let's assume that this is here is for B. Okay. For flip-flop B. So I'll have to take a look at this guy in here and this guy in here. And if you fill them up, you're going to see that it's actually 0, 0, 0, X. And then here I have 1, 1, 1, and another X in here. Okay, and the last one is actually just, I'm going to call it Y in here. So for this Y, it's actually these guys in here. It's the current state of A and B and the input and whatnot. So you can see at X0, it's a bunch of zeros. So I have 0, 0, X and 0. And for this one here, I have 0, 0, 1, and X. And now all I have to do is just figure out the state equations that we done before. So for example, for the first A, I'm going to say AT plus 1. It's actually just, you can technically like figure out what you need to put with these zeros or ones or whatnot. Like whether you want to treat these X's don't cares as zeros or ones as you've done before, or I'm just going to keep them as X. What I'm saying is you can specify them as zeros if you want to, so that it goes to the reset state if you want to. But anyway, if that's the case in here, you can write that A of t. It's just basically, I believe it's B. Let me just do that here. It's the current value of B X bar. And of course, for this particular B in here, we're gonna have to have, I will do it that way here. It's actually just the whole thing in here, which is just X. That's simple, okay? And then the last one, which is Y in here, I will deal with it. It's maybe this one is the best option for us. It's again, it's not the only option, but it's probably the good one. It's A and followed by an X. All right, so the last step is actually drawing the schematics or the logic diagrams for this particular circuit, and it's a pretty straightforward procedure in here. All right, so the step involves, well, I need a couple of flip-flops. So what we need to do is we need to say, okay, here's a flip-flop, okay? And here's another one, for example, in here. We need one for A, one for B, for example. All right, so this is, let me just call this B for the sake of simplicity, and this is A. And then we're gonna have to figure out what the input for A is, just B X prime, okay? So that means I have to take this one here as B, I'll put it with an AND gate in here, and then here I'm just going to say X, and I can do this circle in here to tell me that it's X prime, and that is actually what is in the input of A. For B, it's much simpler, it's actually just X. Okay, and of course they are clocked signals, so I'm just going to say, or clocked flip-flops, so I'm going to do that in here, and that's the input D for the flip-flop, that's the input D. Okay, what about Y? Well, Y is actually in here. Y is just, I'm going to take A, and I will also take the X as well. You can just draw it that way, or you can do just write X in here, and that's here, and that will be Y, and that will be the whole implementation for this part. So this is a sequence detector that should detect a 1 followed by a 0 followed by a 1, and it's immediately It's a melee machine because this particular line in here, the X appears directly in the output. So the process of designing a more output for the same sequence detector is really similar. So again, I gave myself a few inputs and outputs in an example. And in here, I'm just shifting the output by 1 just to indicate that it's a more machine. This is just common. You'll see it everywhere. That means it's on the next clock cycle is when that output will be asserted, when the output Y will be asserted. Okay, so, and again, what I'm looking for is a 101. Here's that, and you can see that the output is in the next clock cycle. This is 101, and the output is in the next clock cycle. And here's another one here with that particular overlap, and it's also giving me that with the next clock cycle. So this is the type of inputs and output I'm expecting to see for a more machine or more output. So let's go through the steps. Again, the steps are very similar to the first one. It doesn't matter whether it's a melee machine or a more machine. Generally speaking, I do tend to see if I'm designing a sequence detector, it's just more as an extra sequence or an extra state. Anyway, let's get started. So we're going to do this here. I'm looking for, just so that I can remind myself, I'm looking for 1 followed by 0 followed by 1. I'm going to say, well, if I have, let's say, if I have a state here, okay, that's basically here as the reset state, S0, so usually you'll see me doing that. Okay, and now the output in here, I'm just going to, because it's a more machine, the output is usually tied to the state itself. So I'm going to say that the output is 0 because nothing has happened. And if I get an input 0, that's not part of my sequence. So I'm going to just stay in the same situation. Now, if I get a 1, I want to remember that because it's part of the sequence I'm looking for. So I'm going to just say here, okay, here's another state. I'm going to create another state that's S1. And the next, the S1 can be reached from S0 just with an input of 1. And of course, the output has to be 0 in this particular case because I still haven't seen 1, 0, 1. Right? And then as usual, you can definitely stop here and figure out what happens if you get a 0, what happens if you get a 1. But I usually go through this whole sequence and then go and fill out the rest of the arrows or transitions. So what I'm looking for is a 0. Hopefully you go in here, okay, and then we do that here. All right, and I have an S2, and that's basically 0. So I'm going to write it on the side in here. I believe S0 just remembers 0, S1, I believe it remembers the very first one, and S2 remembers, I think, 1 followed by 0. The output has to be 0 at this particular point. And now what I need to do is I need 0 followed by 1. You can technically go and tell me, well, I should go in here. However, because the output is already decided as a 0, so I'm gonna have to create a new state. That's different from the melee state. In the melee, we went all the way to S1, but S1 already decided that the output is 0, so I can't use it. So I'm gonna create a new state to actually capture this. So now the state here, I believe it's S3. So S3 in here will tell me, okay, so if you have this input as a 1, so S3 is actually remembering 1 followed by 0 followed by 1. All right, so now all I have to do is just say that the output should be 1 in here, and I believe sort of done. All I have to do is just fill out the rest of the arrows or the transitions. So let's stop. I think S0 is done. I have the 0, I have the 1, S1. I have 1 input, so I have to have from each state, there should be 2 arrows leaving that state. If I had 2 inputs, I'll have 4 arrows leaving that state. But anyway, meaning like all I have to do is just fill out the rest of the arrows for this particular state. So I already figured out what happens when 0, what happens if 1. Well, it is remembering a 1. So I think it makes sense just to stay in here. So I've seen the first one, 1, 1, 1, it's here. And now let's say S2 in here. I've figured out what happens when it's 1. What happens if it's a 0? If it's a 0 followed by 0, well, I think a reset would make sense at that particular point. So I will actually just go in here and say, hey, let's do that in here. I think that makes sense. You go back to the reset state, like as if nothing has happened, and then you go from there. That's S2, so we have 2 arrows leaving. So for S3, I don't have any arrows leaving, so I'm going to have to figure out what I need to do. So it remembers 1 followed by 0 followed by 1. What if you get a 0? Okay. If you get a 0, that's a 1 followed by 0. So really, that should be here. So if you get a 0, that makes sense, I believe. Let me just think about it. It's 1, 0, 1, and then you get a 0, 0. No, that doesn't make sense. So let me just do that one here. So you have 1 followed by 0 followed by 1. What if you get a 0? So if you get a 0, I need to see that I got a 1 followed by 0. Well, according to that, 1 followed by 0 is S2. So all I have to do is just say, all right, I think that makes more sense now. So if you get that here is S2 is 1 followed by 0. So it's 1 followed by a 0, okay? And then you get a 1, you get back in here. So 1, 0, 1, 0, 1, 0. That's actually allows the overlap. What if you get a 1? So it's a 1 followed by a 1 followed by 1. So I think you can go in here because this is actually the 1 in here. And I think that now completes the whole state diagram. All right, so I have the more state diagram at this point. So now the next state is to code these with some sort of a binary code. Again, I can use 4 flip-flops, 1 flip-flop for this, 1 flip-flop for this, and 1 hot encoding or binary encoding. I'm just going to do binary encoding for that particular case. Of course, you can do the state reduction, but I'm just not going to do it. So the binary encoding, let me just fill that table. All right, so here's the state table. So the state table here, all I have to do is just like I decided to use binary encoding for the S0 to all the way to S3. Now I'm using all of them, so I have to just fill them. And really all I have to do is just follow here. So I'm going to show you S0. So S0 telling me if you get an input as 0, you need to stay in S0. And if you get the input as 1, you need to go to S1. So I'm just going to do 0, 1. And I'm going to fill the rest of the table this way. Okay, so I filled out that state table here. So of course you can pause the video and just follow it. All I did is just follow these states in here. So what's the next step? Well, the next step is selecting a flip-flop type and figuring out how we're going to implement it. But we decided to stick to D flip-flop. So all I have to do is just figure out what we need to do for A flip-flop, the B flip-flop, and the Y as an output. So all I have to do is just like, I have 2 flip-flops and 1 input, so I need 3 variable Kmaps. If we have more variable, let's assume I have 3 flip-flop and 1 input, we need the 4 variable Kmap. But anyway, so all I have to do now is just fill it out. So if I decided that the first one is actually for A, so that tells me that AT plus 1 should be, well, I have to fill it. So according to this one here, whenever X is 0, I have to do 0 followed by 1 followed by 0 followed by 1. And then when X is 1, I believe for the A, it's actually 0 followed by 0 followed by, I believe this is a 1, and then there is a 0 in here. Okay. All right, so now we can just reduce all the equations and everything. I think we need to do this and that. And if you write the equation, you'll see that that is actually just, I believe it's B X bar plus A B bar and X. And we can do the very same thing for flip-flop B. So that means I'm targeting these guys in here and these guys in here. It seems simple. It seems 0, 0, 0, 0, 1, 1, 1, 1. And in this particular case, it tells me that BT plus 1 is just basically X. And the last one is actually, I believe it's the Y in here. And the Y is also simple in this particular case. I don't have the X, so technically really I don't need, for the Y, I don't need the 3 variable inputs because X doesn't affect it. So really all I need is a 2 variable input, and frankly speaking a 2 variable input is just a gate. So let's see what type of gate it is, or not always it's a gate, but in this particular case it's 0, 0, 0, 1. Whenever these happens, that's just the AND gate. So really Y in this particular case is A and B, or the current value of A and B. So what's the next step? Well, the next step is just to draw that circuit in here, and we can figure out how to do it. It's just a flip-flop followed by another flip-flop. I'm just going to call this is my A, this is my B. Of course, these are clocked, so I'm going to write the clocks in here. So what's the value for B? Well, B will just get the X. How about the A? The A is a little bit more complicated. It'll actually take the value of B in here into an AND gate, okay, not with an X in here. And then we're going to do these here with some sort of an OR, and the OR will get 3 signals, or it's actually 1 signal, but it's like 3 ANDs. So you get the value of A, which is from here, and the value of B bar, which you can just take from here and input, or B bar in here, the Q bar, and then X. I'm just simplifying it by writing it this way. So the final step is actually to figure out what the output is, and the output really is just A and B together, and that will be Y. And this is the more implementation for the 1, 0, 1 sequence detector.